experiment. Experiment 15, which is reduction of a ketone. For reduction of a ketone, your reactant is fluoroanone, and the product is going to change to alcohol, so you would get the fluoranol. The reactions that we have up here on the first page, we have the ketone, and you have the final product. The functional group of CO double bond is changing CO double bond. What is the reagent that is used in this reaction? The reducing agent that you are using here. Sodium borohydride. Yes, sodium borohydride is the reducing agent that you are using in this reaction. What is methanol? What's the purpose of using methanol in this reaction?
Methanol is gonna attack.
Louis, please use the chat. Methanol is going to be used as a base, right? It will be used as a base to abstract the H plus at the end, but to begin the reaction is a solvent. You have two solid compounds that you are starting your reaction with. You cannot mix two solids and expect a reaction. Your reaction media is a liquid, so you have to actually dissolve your reactant, dissolve your reagent in a solvent, proper solvent, and in order for the reaction to happen. And it happens that your solvent, in this case, because of the pair of unshared electron you have on oxygen, can actually abstract the hydrogen at the end, or whenever it's needed. It can also act as a base. The experiment is going to take like 30 minutes to complete, or about 30 minutes to complete. So for that reason, I'm going to start the experiment. And for the half an hour that we have time, we will continue discussing about the experiment and the other techniques that we are using. So we are going to measure 1.5 gram of the fluoranone in 30 milliliters of the ethanol. So ethanol and methanol is the same. So we are using ethanol in this based on the procedure with the magnetic stir bar, and we are going to mix it. So first we are going to do the measurement for fluoranone and our so 1.5 grams of see the 1.5 grams of the fluoranone. I'm going to measure that. Fluoranone is a yellow color compound. Just adding enough to make it 1.5. Okay. I want you to take a screenshot of the mass of the fluoranone. Do you see it? Okay. If you can see, take a screenshot, please. It's actually 5. No, you cannot see it? Okay. Let me see if we can. Better? Good. Take a screenshot. Okay. And I'm going to add the solvent, which is the 30 milliliters of it. Adding the 30 milliliters of the ethanol, and we're going to stir, try to dissolve it. And measure 0.2 grams of sodium borohydrate. I'm going to measure the 0.2 grams of sodium borohydrate. Let me ask. Do you have another container for sodium borohydrate? But this is all liquid. Okay, we had problem with the chemicals yesterday, and it looked very like colorful, and I thought that it's contaminated. This compound, it looks like, has been left open also, but we were lucky yesterday. Actually, we got very good results, very good result of the experiment. Trying to see if we have another container. If not, I'm going to start anyway with this. Thank you. It's good. This is good. Thank you. Okay. Okay. Trying to cut the large piece so I can get the 0.2 grams. You're wondering what I'm doing? Good thing we had another container that was not. Okay, it's looking better. So it wasn't liquid. The other one, it turned liquid, and most likely it was due to the temperature of the room. That's what actually, at least they told me. Okay, and keep this for 30 minutes. Stirring. What would be indication that the product is forming while this is stirring? What are we looking for? Color change. What color do we expect? A yellow color going to white color, because the product is going to be white color. We expect for the yellow color to disappear and white color to appear. So we are going to continue with that. The compound that is forming our product is not soluble in ethanol. And since it's not soluble in ethanol, it's going to also show precipitate. So precipitate would form. It should turn cloudy and with white precipitate. Adjust the stirring to make sure that it's consistent. I may have to change this. When I change the setting on this stir, it doesn't behave. So it looks like the problem is the stir. Okay, this one is better. It's consistent stir. Good. What is the next? The product being 9-fluoronone? No, that is the reactant. The reactant is the 9-fluoronone, and your product is going to be alcohol, so is the fluoronol. Yes, fluoronol would be the product. After we see the white color, what is the next step? So basically the step 4, like we kind of, at this point, we assume that we will have the white color. If we don't have white color, we add more. And after we have the white color, what should we do? What should be the next step? Using up HCl solution. What's the purpose of using HCl solution in this experiment? The iced HCl solution. Yes. What's the purpose of using HCl solution? It gets rid of the unreacted sodium borohydride. So there would be HCl is used to destroy the excess amount of the sodium borohydride. Very good. And when sodium borohydride is being oxidized or being when it reacts with the HCl, basically sodium borohydride has a H minus, because hydride is a H minus, H plus is a hydrogen ion, and H with no charge is like hydrogen atom with 1 electron. H2 is hydrogen gas. So H minus from borehydride with the H plus from HCl is going to combine, and it gives you H2 gas. And that H2 gas that is forming is going to foam up the mixture, is going to form lots of foam, and that's due to produce a production of the or H2 gas being one of the products. So you might see the foams that is forming with the by adding the compound, the mixture into the HCl ice solution. Okay, how do we identify the product today? Okay, we are using IR, and how could you use IR to identify the product today? Can use the melting point, and we can use the IR. IR is good, but how could you look at the largest peak? You have to basically compare the reactant with product. So when you are using this in your discussion, like information in discussion, in conclusion, you have to say what is expected to, what is the major peak that expected to have for reactant, which is a ketone, and you would have a peak at 1700, but the product, it should change to alcohol. So the peak at 1700 should disappear, and a peak at 3300, which is a broad peak with a round tip, that's the indication for the OH, and that's how you recognize or prove that product has been formed. So a broad peak at 3300 with the round tip is going to indicate you have alcohol as a product. Disappearance of the peak at 1700, it will prove that there is no impurity with your product. So the product should not have a peak at 700. Your reactant, because that's the indication for your reactant. Every other peak, those are not the only peaks that you are going to see on the IR spectrum, but other peaks that you have for CC single bond, you have for CC double bond, is common between the ketone and the alcohol of fluoronone versus the fluoronol. Every other peak is going to stay the same. The only difference, so we are looking for application of the IR when we are using for our reaction. The application of the IR is to use to monitor the reaction. As that when we monitor this reaction, we are looking for disappearance of the CO double bond and appearance of OH bond. So the product, if it shows only the OH bond and not the CO double bond, that means your product is formed and the product is pure. Now, if it doesn't, if the CO double bond does not disappear completely, what does it mean? So you get your product, you get the IR for product, you see peak at 3300, and you also see peak at 1700. What does that mean? You have an impure product, and what type of impurity is going to be there? What would be the impurities? The impurity would be sodium borohydride, ethanol, or 9-fluoronone. So you would have some leftover of the ketone still in your product. So to remove that, you want to, there are two ways you can do that. One, you can take a IR spectrum of the product right after filtration. If the peak at 1700 disappeared completely, you don't have to do recrystallization because there is no fluoronone left over. Or you can do the recrystallization and make sure that the impurities is gone. Then you take the IR spectrum of your product to hope that there is no fluoronone left. If your solvent, which is the recrystallization solvent, proper, is not going to recrystallize any of the fluoroanone. Since I mentioned today about the monitoring of reaction using IR, I'm going to practice that first. I'm going to take the sample of IR of the sample before recrystallization, and I will show it to you. If the sample doesn't have any, if the sample doesn't have the product that we have after filtration, doesn't have any CO double bond, then we are sure that it's going to be pure, and we don't have to do the recrystallization. But if we have leftover of the ketone and the PCAT 1700 is going to be present for your product, then we have to do recrystallization in order to purify the compound. Okay, any question about the experiment? Any question about the pre-lab questions? The yellow color is gone, yes. How did we, you set it up to 137, so 137 is going to be, yes, it is just, it's very actually fun to watch and see what is happening. Like yesterday, as soon as I poured the sample over the ice, that I wasn't expecting to have the methyl, the nitromethyl benzoate product. When it did precipitate, actually, I got so excited because I was thinking my compound, my reactant is contaminated. I'm not going to get the product. But when I got it, believe it or not, after doing this experiment for so many times and watching my students doing the experiment, I got more excited than even if they brought me food at that point. So it was nice. And now you see the yellow color has disappeared, the white color has appeared. It appears. If I do this like for longer time, I'm not going to let it pass the 30 minutes. But if I be patient now, it might help me later. Because how is going to help me later? Because when I do the first IR, if I don't have the peak from the from CO double bond, then I don't have to do recrystallization. Remember, for recrystallization, I have to do 5 minutes of icing, 5 minutes of vacuum filtration, and 5 extra minutes of the of drying the sample. But if I don't have to do recrystallization, I'm saving there like 30 minutes of the time. So it's worth it for me to wait longer to make sure the reaction is complete first place. So I may not have to do recrystallization today for this product. And I want to do recrystallization if there is no PCAT 1700. I hope it makes sense. Okay, who has the timer? Did someone set the timer already? It should go to 137. 15 more minutes? Okay, I'm going to wait at least 5 more minutes. Thank you. I'm going to wait for at least 5 more minutes because it's been white color for a while. So to wait for 5 more minutes, and then I can. While we are waiting for the 5 minutes, it's good for me timing for preparing the cold HCl solution, and for you to take a screenshot of the setup. I just want to make sure that the camera catches the setting. Please take a screenshot of the reaction mixture as it's turning color, because we saw earlier the other screenshot had the yellow color. This one has a white color. It shows the progress of the reaction also, as well as helping for your attendance. It's the color change. We don't have to time it exactly, because the shade is not like titration. The shade of the yellow color, it goes like low and low, but is is at least is an indication that the color. I didn't keep track of the exact timing that it went white color. To answer your question, I don't have that number. But normally we keep like for 30 seconds, for 30 minutes to make sure the reaction is complete. You're welcome. Okay, let's go ahead and prepare the iced HCl. Under milliliters of ice and 5 milliliters of concentrated HCl. If you take the ice, because there's like a crushed ice, you have space in between, it's like you fill it up and then you add water, it actually comes down. So sometimes it's tricky, like how much ice you have to take. You want to make sure that you have enough ice to build at least 100 milliliter of the ice water. So don't measure the volume for the ice, we measure the volume for the ice water. Okay, I'm going to add the HCl when I put my gloves on. Okay. Should I stop it now? Because it's been boiled for more than 10 minutes. I can stop and take it to the fume hood so I could add to the HCl solution. You can take a screenshot of the reaction mixture at this point And notice that the foams are forming because the sodium borohydride that we have is reacting with the HCl, produces hydrogen gas. Okay, what is she pouring? Okay, which step are we in now? Which step we were? Step 6, okay. So I had my reaction mixture pouring into cold HCl. But make sure to get all the product transferred. So I'm washing with some. So make sure you take a screenshot. I have to wait for the ice to melt before I can filter it. So we have our product now, and because of the HCl, I'm sorry, because of the hydrogen gas, and after adding the HCl, it formed a lot of foam. It's a little bit more of the product attached to this flask. So I'm going to just wash it with some ethanol or methanol and transfer. Okay. Now, next step. What's the next step? Vacuum filtration. Set up the vacuum filter for I use watch glass, please watch glasses. Have the mass of the watch glass and filter paper. Do you see the number? 50.065. Watch glass and the paper, yes. Use the set up the vacuum. Just using some cold water to make this stay still. Today is one of those days that I may have to stop the vacuum to empty the vacuum flask because I don't want too much water to get in. So I don't want any water to go from this side arm to the trap. Trap is okay, not too much of a trouble, but we don't want any water to go to the pump. So I have to be careful with the volume of the solution I have here. Vacuum is not very strong, but hopefully. It will take some time because the vacuum that we are using is not very strong. Okay, let me see if there is any question that came up while we are waiting. Vacuum filtration, normally it's faster than this one, and it's always much faster than the gravity filtration. But if the particles are small, it can stuck in the opening of the filter paper, and also it's like foamy and too much of a liquid. Not very strong vacuum. That's why it's taking more than usual. Okay, very good. Need to wash the product with cold water. And because 2/3 of the flask is filled up with water, I have to stop the vacuum filtration, empty this, and continue again. You should always wash the product with the solvent that you're using to make sure all water soluble impurities are being removed before recrystallization or before doing anything with the product. Drying of this sample is going to take much longer than the other samples we have, but while this being vacuumed and dry, I'm taking a small sample to the IR to get the IR spectrum for the crude product. As I promised, if we don't have obvious CO double bond, we don't have to do recrystallization today. I use like absorbent paper, which is basically filter paper, to get the moisture out, to dry the sample before the IR. The vacuum can run here, and we're going to the instrument room to find the IR spectrum. If you bring the spatula. There's a software or program that controls the IR machine. IR has a light source that you shine the light in the IR region through your sample. There is a sample holder. The sample holder is right here. We place the solid sample, and we would tie this like a finger tight to get very thin crystals or plate for the of the sample, and we actually put lots of pressure, finger tight, and the machine tells us when is enough. Actually, the program would tell us when is enough. The light is going to pass through the sample, and light is going to be absorbed at certain wavelengths. Those wavelengths, they represent the functional group of the compound. Okay. Going to and this is the reduction. Going to get my sample ready. Okay. I'm using very small sample of the product, very tiny, and place it in the sample holder. Spectroscopy techniques, they are non-invasive. That means the sample that you are using is minimal, and you can actually, after this, determining the IR for your sample, you can actually recover the sample. You can take it out and do melting point with the same. So it's asking for the name of the sample. So I'm giving a name for the sample. We have to apply pressure. As I am applying pressure here, in the computer screen, you see this green bar. That's like, that is good enough. It should not reach to the end because then I can break the crystals here or the machine. And I'm going to scan. When you click a scan, that means start passing the light through. It's going to scan 4 times. It's going to scan 4 times, and it takes the average of the peaks. The program allows me to add the peak numbers for the peak, because otherwise you have to use rulers and you have to use numbers like estimated. But when I add the peak numbers here, you can actually see the numbers. You just use the numbers that is provided to you. When I talked about major peaks, those are the peaks that they pass the line of major ones. Like it has to be like they're the majors. Comparing the 1411 here, 1451 would count as the major peak. So we have 1, 2, 3, 4 major peak here for this compound, and we have actually this one is a major peak because it's reaching to the baseline. So major peaks only is like 4 if you want to identify. But when you use the comparison of reactant to the product, we are looking for point of difference only. So we are looking for the peak that appeared at 3300. What else are we looking here? What else are we looking on the IR? The 1700, we want to make sure that 1700 is visible or not visible. Okay, if it's not visible, and we see that between like 1600, 1800, there is no major peak for the ketone, because you saw this already when you have a ketone, because it's a polar bond, it's going to be very strong. This was the ketone you had last class for the CO double bond, for ester, is going to be like this sharp. So we don't see that at the 1700 here. That means there is no leftover of ketone. Which one do you want to see? That screen or the paper that I had? This is from last class. This was for ketone. So if you were going to have a ketone, you would have had at 1700 a sharp peak like this. But what is on the screen now, it's good that we don't have any peak at 1700. That's the 14, 16, 1800, and then we don't have that sharp peak. I'm going to print this to make sure that I have a printout. And also, I'm going to scan this from the screen. Sometimes it gives me better picture to email it to you for your record. Based on the IR spectrum I have for this product now, even though it's a good product, it's showing that I don't have to do any recrystallization because I don't have any ketone left. So I'm going to bring my phone to get the scan of that spectrum. Okay, going to scan. Maybe this picture is going. Is not the best? The best thing would be to have the printout and work with the printout for you, but it's at least. And if this computer was connected to Wi-Fi, I could have actually sent the files, but they don't want this computer to be connected. I cannot use that computer to send it to you. Okay, I will send this IR spectrum to you. I have a printout also. I printed out for record, but that is you need the electronic copy. So I will send it. Next step. Oh, before I leave, I have to make sure to clean the machine. Cannot leave this. And what I have here, actually, I can use it for melting point later. It's non-invasive. It's actually, it didn't use the chemical. Just the light passed through. It didn't decompose or affect the chemical. Just trying to show the advantage of using spectroscopy. It was very fast, so that's how long it took for us to determine this is a alcohol, not ketone. It wasn't us actually, it was the machine, but at the same time, it doesn't use too much of the chemicals. So it's a good technique. Non-invasive and fast. Two major advantage of using the spectroscopy technique. Sample. Next step would be to get the melting point. Just hope that I can get the melting point today. Sometimes the sample doesn't dry well because it's all fluffed sample. I'm going to place this in the oven. We have a big sample size, a large sample size here. Gonna have to this sample here, we always have trouble drying this sample. Sometimes I have to leave it overnight for it to dry to give you the mass of the sample. Other times I use absorbent paper and get the moisture as much as possible out. Absorbent paper, you just take like paper towel, you wrap your sample, a filtered paper that is clean and it won't be contaminated, and you place it between layers of paper towel and try to get the moisture as much as possible. So by pressing the sample using layers of paper towel, you can get most of the moisture out, whatever was left there. So it would make the drying process faster. Do you have the melting point for the product? Do you have the melting point for the product? The literature value, we have not measured the melting point. I'm asking you if you found or searched for melting point of the product. Still is moist. Okay, one second. Okay, it still is moist. I'm just using more papers to get the absorb the moisture of the sample. Taking extra papers out. The only thing that is left is the filter paper that we have the mask from before. And I'm going to place in a watch glass, place in the oven for it to dry. I have bad experience with this sample. It takes a long time because you saw how the product was foamed because of the hydrogen. And sometimes I let the students to keep it to next day to measure the mass or measure melting point. I will try later after I measure the melting point. We try the mass and you're going to, after you calculate your percent real or theoretical, you can see if it's too much is because it's not dry. But I used a good sample size. I left in the oven. The same sample I used for IR, I left in the oven, and now we can use that sample for a melting point. So I'm leaving the sample to dry in the oven. But the sample that I used for IR, I had in the oven. It looks dry. We can do the melting point with this sample. Okay. Looks dry. So okay, going to feed the sample into capillary tube. I hope that it's dry enough. I can do it. That's not bad because the sample is moving in the capillary tube. It makes me believe that the sample is dry. Otherwise, it would have stick to the top of capillary tube, and if I drop it, it wouldn't come down. So good. Have the sample. Place in sample holder. What should be the setting on the power regulator? Using this chart, what number should I place? What do you think? Hard to see the numbers. Okay, here starts with 1, 2, 3, 4, 5, 6, 7, 8, and 9. Here we have 50, 100, 150, 200. Between 3 to 4? 3 to 4, that would be if it's melting at 100, right? Between 3 to 4. Because it's melting at 150, I think you are safe to put between 4 and 5, right? So 4 and 5, because didn't you tell me that sample melts at 150, around 150? For 150, 5 is good. Okay. So I'm going to place it between 4 and 5 and wait for the sample to dry. Whatever is left of the sample from the IR and the melting point, I'm adding to the other sample so we don't lose the sample before we measure the mass. Too much of the sample before we measure the mass. Do you have any questions for me? Any questions, everyone? What's the melting point range? Not yet, please, it's still recording, but you can type your questions. Is the wash with DI water 2-3 times? Yes. And I put the water into the beaker and I poured it over the sample. Yes. What is the range of melting point? Anybody has a range for melting point? How would I get the range for melting point? I have to wait until it's melted, right? Is your sample melted already? Or we are waiting for it? Okay, that number is a theoretical value. But I just put the sample in the melting apparatus and I'm waiting for it to warm up and I keep looking at this to see when it's melting. I do not have experimental value. What you're giving me, those are literature value for the melting point. So I'm waiting for the value for melting point. Mass of filter paper with the watch glass, you should have either a screenshot or go up on the trail for the chat. It's recorded there. It was 50 something. I don't remember. I didn't write down, but it was 50 something. It's not melted yet, which is not too late. The temperature is still between 80 and 90. So we are waiting for the sample to melt. Okay. Any other questions? We are still waiting for the sample to melt. Are we going to have a mass of filter paper and the product? Yes. Yes, we will. We cannot measure the mass before the sample dries up completely. So I left the sample in the oven to dry before we can measure the mass. We cannot measure the mass before it's dry. It's good, but you're kind of moving ahead of the actual time for the experiment. We have to wait. We have to wait to get the data for melting. We have to wait for measuring the mass after the sample is completely dry. The temperature is 120, but has not melted yet. So just reporting what I see here for you. Is 135, has not melted yet. So I'm just reporting. Yesterday I keep saying it's good, and then I had to explain why it's good that it's not melted. So I'm going to explain now, because the melting range, the literature value for this sample is around 150. Boiling point of water is 100. If it melts below 100, is going to show that it's been dissolved, actually not melted. The sample is not dry. So we don't want the sample to melt below the boiling point of the solvent we use for washing. Okay, very good. Initial melting 146. 146 for initial melting. 148 for the final melting. And take a screenshot of the melt temp apparatus for your screenshots. I don't know how many we have, but at least if you missed the last one, you could have one here. Okay, going to turn it off and take the sample. It's melted already. Bring back to the lab. Trying to work on mass for the compound. We have to make sure the compound is, the final product is dry before we measure the mass. I try to be efficient and use up the time properly. As a student, I did the same. As a teacher, I'd like to do the same. And now I'm acting a student, performing an experiment for you. Okay, the sample is not dry yet. Okay, I could feel it. Still is moist. So I'm going to give like couple more minutes of time in order for sample to dry. So we have few minutes, couple more minutes at least. Okay. I'm going to stop the recording at this point. The experiment is not done yet. I have to do the measurement for the mass, but I'm going to use the time now to call for attendance. And for calling attendance, I like to turn off the recorder. And then I could answer your questions also. We continue with measuring the mass for the product and answer your questions.